Right, some of you may have been aware of this technology. What I wanted to do today was to really give an overview of all the different applications that this new technology can be used for. Quite often when I give talks on this, I have to limit myself to the specific audience I'm speaking to, so whether it be geophysicists, petroleum engineers, completion engineers, but bear with me, I'm going to try and do all of it here to just show how they're all interrelated with this one technology. So this is basically, hopefully you can see that, yeah, this is basically all of the different applications. You'll be pleased to know I'm only going to do a few slides of each, but there's quite a bit to get through, to show how we can use this technology for everything along the entire life of the well. So from the construction phase through to completions, into production, and then on to abandonment. And how the different phases of that, from hydraulic frac profiling, the microseismics, the passive seismicity, flow monitoring can all be done. And you'll see this slide. I'll keep referring back to this slide as we go along. Very briefly, kinetic. One of the important things to say about DAS and fibre optic technologies, an important thing I think, is this is really a homegrown technology. It kind of all came out of the UK, and there are a number of companies really leading this field at the moment that are UK based, and hopefully, you know, long may that continue, and we don't go and sell it off to some other countries. But we've had rapid progress. You know, we're now about 180 people strong. We've got offices all around the world, and we're kind of building the base of the technology as well. So we acquired some optical companies. There's a company called Rio, which is, that's not working, is it now? There's a company called Rio, which is based down in California, which develops the special laser that's used in these systems, and also some seismic capabilities now we've got to actually process the end results that we're getting from here. So, for those of you who don't know, what is distributed acoustic sensing? Well, many of you'll have seen sensors on the end of wires, and some of you may already be aware of sensors on the end of fibers. You may have pressure and temperature gauges, for instance. And they've been around for quite a long time now, 15 years, fibre optic pressure and temperature gauges. And you can quite often put those into multiplexed arrays of one form or another. But the thing about DAS, or Distributed Acoustic Sensing, is the entire fibre, it becomes the sensor. So we can listen at every point along that fibre. And the huge advantage is that means we can deploy that fibre on the casing or on the production string, or use it in, for instance, a wireline or a slickline arrangement, and we can measure the entire wellbore and every point along that wellbore. And this is a typical fibre optic cable. From this distance you probably won't make it out, but just one of these fibres, every result I'm going to show you from now on is just taken on one of these optical fibres on a cable that runs down the wellbore, and that cable can be, the longest well we did was 7 kilometres long, so you can see the range it can go over. And the resolution, as I say, I can look at individual portions of that fibre simultaneously. So if I split this fibre in arbitrarily, let's say, into 10 metre gauges along a 5 kilometre fibre, I have 500 independent, simultaneously sampled sensors that I'm now looking at. So it becomes an array of sensors, microphones, if you like, that we're using here. So how does it work? Well, it's based on a principle called Rayleigh backscatter. Same thing that makes the sky blue when you go out in the daytime. What we do is we fire a pulse of light, a very coherent pulse of light, into the fibre. And there are some very small inhomogeneities in the atomic structure of the glass, the silicon glass that makes up the fibre. Now, the glass fibre is probably the purest material man has ever made, but still there's enough to cause a very, very minute amount of backscatter. And we measure that and we capture it. And you can see as the pulses go through the fibre, we get this, what appears to be a random backscatter pattern. But the good thing about that pattern is it doesn't necessarily change if it's not disturbed. What does happen, however, is if you put multiple pulses back down there, if you then insonify or in some way put a signal onto one part of the fibre, you get a change locally at that backscatter. And because you can measure the speed of light in the fibre extremely accurately, so you measure that time, you know precisely where it happened, where that event occurred in the fibre. So fundamentally, this is a strain gauge. That's the thing to understand. What you're looking at here is you're looking at strain within the actual fibre itself. But it's so sensitive to strain in the pico region, kind of the pico strain limits we're looking at here. We can quite easily pick up pressure effects and particle velocity, particle displacement effects that are happening due to seismic signals. So the other big advantage is that means I can deploy this relatively thin cable. I can deploy in a whole host of different areas. So if I want, for instance, I can put it behind the casing, and for that's where I put it if I want to measure completion operations. So if I'm fracking my well, for instance, I'm going to be sticking an awful lot of proppant and water down that well, so I don't want the fibre inside the well. Therefore, I put it in the cement behind the casing. For most jobs we do, we tend to attach this to the production string. But as I said earlier, you can also use it in a temporary intervention. You can put it on a coiled tubing, wireline, and there are now actually carbon rods with fibre in the middle of it, so you can insert a carbon rod into the actual wellbore itself, a bit like the old chimney sweep situation. And you can see in the video there, maybe a bit small for you, but you can see in the video, the installation is actually quite quick. There is a lot of work going on at the moment of how to improve this installation method by high temperature cable ties and also steel clamps that can be used. There we go. So upstream examples. So before I get into discussing all of the applications we're using downhole, I just wanted to very briefly mention all of the other applications in the oil and gas space that we use this for. This is a platform technology that can be used for a whole host of different things. So one of the key areas that we look at, for instance, is pipeline monitoring. We're currently monitoring around about 12,000 kilometers of pipeline worldwide, and that's putting our interrogation unit onto communication cable that runs next to pipelines. And what we're able to detect is third-party interference, people doing hot taps on pipelines and also leaks in pipes as well. But we're using it for perimeter detection. We're beginning to explore this technology for surface applications, so life of field seismics and permanent reservoir monitoring offshore. And then there's condition monitoring in risers, vortex-induced vibration of cables, subsea cables that can occur, and a whole host of different other condition-based monitoring applications. We're also beginning to look at other forms of sensing, such as magnetic field sensing. But that's really not the focus of the talk. The focus of the talk is what we do in upstream, downhole, and how we use the technology. So through this list, I'll start with VSPs, the vertical seismic profiling, how the technology has been used in this area. Now bear in mind, the first measurement ever done in this was 2009, so you're only really looking at 5 years of development activity, and in that time there's been huge progress that has been made, and we believe it's going to continue as well. So what's the advantages of VSP using fibre? Well, in a traditional VSP, typically you would drill an observation hole. You've got intervention in your well, you've got craneage on the surface, it's expensive. If you're going to put the geophone array into your well itself, which you might choose to do, that's risky, as I say, expensive, and you probably have to move the array several times and keep reshooting to get full coverage. The beauty of the DAS system is you actually have that fibre in the producer or the injector, and that now acts as the sensor. So I can do all my seismics on that one fibre. I don't have to drill an observation hole. And the important point to note, of course, is it remains there for the life of the well. So if I want to come back and reshoot and do time-lapse seismics, now I've got the means to be able to do that. So the conventional way is high pressure, it's risky, it's expensive, whereas the DAS approach is low pressure. There's no well intervention required for this, and it's a safe and repeatable operation. So every one of these shot gathers you'll see here on the right-hand side is gathered on the optical fibre. So as I said, just one of these fibres, and those geophysicists amongst you will hopefully recognise these as pretty decent shot gathers that we're looking at here. So the advantages, as I said, we can get now with this thin cable, we can get in wells which are pretty much inaccessible to conventional geophone arrays. Because it's permanent, my on-demand repeat surveying is much easier to do. I have full wellbore coverage from surface to TD, so I can get better imaging quality from that, and I don't have to keep repeating a survey because I'm moving the geophone up. It's retrofittable, so if necessary, I can work over a well and put this onto a production string and then leave it in place. And I can operate it in some very high temperature wells. So for instance, we're beginning to do work in some SAGD wells, which we're looking at over 300 degrees C operating temperature, and it will be there for some considerable time. So we've done numerous jobs in this area, but I just want to highlight just a couple, really. This is a large job. We've only done one today offshore job, but this is worth noting. What happened in this particular situation, we were doing this job with Shell, as a lot of the work you'll see here is actually based on Shell papers that have been published using our technology. What was happening is there was a big Gulf of Mexico nodal survey in progress. It was a very expensive shoot. We were asked to go along, and that actual offshore platform had 2 fibers in it. These were legacy fibers. They were actually used by somebody else for other fiber sensing applications. But we were asked to go along and attach our box to it to see if we could actually see anything, get any usable seismics. Well, the result of that is one of our employees had to spend 7 weeks on that platform all over Christmas. And he eventually recorded 50,000 shots, 70 million records on 1,400 channels. The reason why he was asked to stay is because the data quality was extremely high. This was, as I say, this was fiber attached to the tubing on this offshore rig, and it went down to about 6 kilometers total depth. And when they've, both Shell and BP have now actually imaged the full 3D data set for this. And unfortunately, there's no papers available, but they have been talking about it in various SEG workshops and the like. And I think at the last SEG workshop, the BP guys were saying that these results were really, really surprising them because of the amount of resolution and quality that they were getting from this. So then we've got repeat. As I say, we can come back and we can repeat these surveys. So this is another example. This is one job that we did earlier this year. We did it in February. This was in Oman. This is an old field, and they need to increase the production rates in this field. So what they're doing is steam injection. But as they're injecting the steam, they don't know where that's going, and they also don't know where the oil's flooding to. So they want to be able to know what's happening there so they can do their infill strategy, their drilling strategy of where they should be drilling in the future. But how do they continuously image subsurface? Well, they tried convention. They couldn't do it using surface seismics because the area is far too busy. It's a brownfield site, extremely busy area. They tried it with conventional VSPs, but that proved to be too expensive and, again, too much surface equipment. But DAS VSP came along and enabled them to do these types of measurements. So what we did is we actually instrumented 8 wells simultaneously. So we had all that. We worked over, took about a month to work over the 8 wells, put fiber on them, put them back, and then we did a month of shooting for the full 3D acquisition over it. And what we're now doing is stitching those 8 well VSPs together to get a field-wide VSP of what's happening there. And you can see everything was built in a shipping container, and you can see the 8 interrogation. Well, in fact, there were 9 because one well had 2 fibers in it. So there were 9 interrogation systems. Each one of those boxes represents the one interrogation system that can interrogate 1 fiber up to 6 or 7 kilometers in length. What we're able to do as well, so that we don't actually waste any, we don't want to add cost to the acquisition by delaying the shoot. So everything was synchronized to GPS, synchronized to the triggers, and we were able to decimate the data to correlate it and to stack it in real time, as well as put the headers on there so it was output in SegWide files. Immediately. So this allowed us to do in-field QC of the data and ensure that the operator was happy with the way we were capturing the data and subsequently processing it. This is the actual shot pattern that was done here. You might just be able to make out the green triangles. This is the location of the 8 wells. The red dot in the middle there just is one shot location. I just wanted to show you this is what we were getting on those 8 wells. So from that one location, you're getting pretty decent shot gathers that we can now process. And as I say, that processing and stitching those 8 wells is now going on. There is another application in seismic. This is quite an old slide now, but this is a CO2 sequestration site, and the technology is being used for the monitoring, measurement and verification of that CO2. So what happened here is this is useful to show the difference between a geophone array in a well and the DAS. So in this situation, there's observation well. A geophone array was lowered in it, but on the outside of that observation well, there was a fibre in the cement. So now we've got, when we did the 3D shoot, we've got a direct, sorry, in this case it was 2 walkaways, a north, south, east, west walkaway. And you've got a direct comparison between the 2 of them, so we can see how they're different, how they're different. And we must emphasize they will be different, because this is not a geophone. This is a new technology. As I say, this is a strain gauge. And so when looking at this data, you have to get your head around the fact that when it's not precisely the same as a geophone. But what it does allow you to do is things like the time-lapse and see how things have changed. So when we came back a year later, we were able to do it again, and we got a normalized RMS of around about 15% on this, which, given the ground conditions, gave people enough confidence to say that this will be used in the MMV program from this point forward. So that's kind of active seismics, if you like. Microseismics, well, yes, we can see the microseismics on that fibre as well. It may very well be the same fibre, and what we can do is we can listen to that permanently and try and pick out these actual microseismic events. Now, the DAS at the moment is not as sensitive as a geophone. We're quite away from that sensitivity. Nevertheless, because of the very large aperture that we've got, we can spot these microseismic events, and we can actually locate where they've come from. So this event is around about 0.5 magnitude, so quite large in microseismic terms. But what's unique about it is you actually see the progress of that microseismic event right the way to surface. And you can see the separation of the P and the S waves. You can also see that it's got a strange velocity profile associated with it, and that's because of that was a highly deviated well, and that accounts for that strange shape. Now, that high deviation in the well actually is very, very beneficial to us, because essentially we've only got a 1-component sensor here. If we have got a deviated well, and if we can see over the entire aperture, what it does allow us to do is intersect the circles and actually geolocate where that event actually came from. So it's kind of a useful benefit of when you've got deviated wells. Okay, so that's the seismic part over. But I can use it for other things. If I then go into flow monitoring, I can use that same fibre to basically switch the lights on in my wellbore and see how that well is flowing. So these images here are what we call waterfall plots. On the y-axis, you've got depth. So top is the top of the well, bottom is TD. You can see on the right where the perforations are, so that's the production zone. And the x-axis is time. So these times are in a matter of hours, or these are typically several hours we're seeing here. And what you can see, these are both gas producers, but you can see the effect of water uploading in the wells. You can see some of the inflow effects that's actually occurring in those well bores as well. And you can see the hydrodynamic slugging that's occurring in that well bore. Information that you simply would not have ever seen. You've normally just got production logging data at the top of your well, so you've got no idea what's actually the dynamic nature of what's going on in the well until you have this technology able to illuminate it for you. One of my kind of favorite slides in this area is this one, where if we look at the bottom, we've just got the production data. So this is typically what you'd get, and you can see the amount of water, the amount of gas and the pressure that you're seeing. But if I look at the DAS, I can see at the top of the well, I can see the actual water, where it's forming, and it's forming at the shoe of the first casing string there. And I can see it uploading to the top of the well as it reaches the top over, in this case, it's a couple of hours. And at the bottom of the well, I can look at a higher frequency area, And you can see little bright spots appear at each one of the perf clusters as we start to produce more gas because we've taken the head of water off. So again, just insights to what's going on, the dynamic nature. And of course, then what we can do is take those waterfall plots and we can just animate them onto the wellbore itself and speed the time up a bit. So we can now see dynamically how everything is interacting with the wellbore. So in this example, you're just seeing where slugs are forming, how slugs are being generated and coming up the wellbore in a 3D modeling way. Okay, so one of the most recent things we've actually done is taken that information and then moved it to a permanent installation. So this now is on-demand flow measurements, if you like, flow measurements without the PLT. What we have is we have now 2 stations, one in Canada, one in the US, and there'll be 3 more by the end of this year, this calendar year. We have in the shipping container there a DAS interrogation system. We also have a DTS, Distributed Temperature Sensing system in there, and this is all solar powered and cogen powered unit. So, oh, that slide's gone a bit funny. Sorry about that. That image has for some reason changed. What we do is we take the waterfall information, which was supposed to be where the 600 is. We take that waterfall information and actually at the site we process that so that we turn it into essentially a traffic lights. So we say when flow is good, we've got green. When flow is like bad or non-existent, we've got red. And where it's intermediate, then it's orange. And this is the kind of graph that it produces on the right-hand side. Now, the important thing to note is that's uploaded to the cloud every 10 seconds from the site. So now I can log in with my phone or my tablet or my PC, and I can see precisely how that well is evolving over at any moment in time. And what that allows me to do is get a real insight into the behavior of the well. So if I was to run a PLT, I would only just get a snapshot, whereas this is giving me a continuous record of what's actually happening, and I can see the trends within that wellbore of the flow. The next phase, of course, is to move that into quantitative. This is really qualitative at the moment, so this year we'll be doing this for in quantitative outputs at each one of the perforation clusters to see where the flow is. Smart well monitoring, we can take the same, these are oil producers, smart oil producers with lots of jewelry along them. We can take the data set that we record, and because it's an acoustic data set, we can look at it in different frequency bands, and that tells us an awful lot about what's going on. So if I look at the low frequency, I can see all the water uploading and how this is a highly deviated well, so I can see water and the oil uploading and it falling back again. I can, in the middle bands, I can see what's happening at my ICVs, my inflow control valves, and at the higher frequency, I can see what's happening in my gas lift valves. So a bit more detail on that. If I look again at these waterfalls, just to remind you, you've got depth down the y-axis, time along the bottom. And you can see at this top one where the ICVs, both ICVs are being shown there. The ICV A at the bottom remained open constantly, but when we turned on the higher ICV, it blocked the flow, and we can see that because the signal where it's coloured, obviously we're getting more acoustic signal. Where it's blue, it's quiet, and we can see that we're suppressing flow. So this gives us that, again, the insight to know exactly what is happening along all of those valves and all of the infrastructure in the well. We also know that the values that we're recording do actually match pressure gauge values. So those ICVs actually had attached to them permanent downhole gauges, pressure gauges. So we're able to measure the pressure. And what we can do is we can overlay what we estimate the pressure to be using DAS on top of those real pressures, if you like, with the gauges, and we find that there's an extremely good match between those pressures. So now, in the future, we hope that this technology will replace those, when confidence is great enough, will replace those gauges downhole. And of course, you can, as I've said before, you can animate it onto the wellbore, but now I can overlay all of the various jewelry I have down there, so I can show how the gas lift valves are operating, which ones are on, which ones have got flow, and the same for the ICVs at the bottom. One kind of Another nice kind of aspect of this is ESPs. The fibre runs, if there's an ESP in your well and the fibre runs next to it, in this example here, you've got surface and you've got inflow at the bottom, but you've got this very big acoustic signal at the middle generated by the ESP. And what we can do is we can look at that in a slightly different way. This is called a spectrogram. So now the y-axis is frequency against time. And what I'm seeing here is I'm seeing all of the switching frequencies of that motor downhole. I can see how fast it's actually rotating. And I can set it going, and I can also notice cavitation effects in that motor. And that's useful for condition monitoring, because I don't really want that to happen. Our background, most of the company comes from a sonar world, and what's an interesting feature is the sixth harmonic of this was very dominant, which indicates to any kind of sonar processor that you've probably got a six-bladed submarine you're looking at. Well, it's obviously not a submarine, so it's a six-bladed pump, which indeed it was. So it just shows you the level you can go into here. So operational issues, when we're looking at fracking, for instance, we can look at things like perfs firing. This is an example of a perforation detonating in the well. You can see the perf at the bottom here detonating, and what you're looking at is a reverberation of that sound up and down the wellbore. And that's useful to know whether that perforation is actually detonated correctly. You can also use it for things like making sure that plugs are set properly. So in this example, the plug gets set in 3 stages. Splines detonate, then the rubber expands, then finally the plug detaches. So there are always 3 events we saw whenever this plug was set, apart from this example where we only saw 2 events. You can see the 2 events here. So we go to the OSR on site, and we say, your plug didn't set properly. He says, yeah, of course it did. I've retrieved the end of my wire line, it's fine. So he carries on blithely fracking the well, and lo and behold, you'll see that the top area here of this waterfall here, this is the actual stage he should have been stimulating, but what was actually happening is he was stimulating a previous stage below that. So he over-stimulated one, under-stimulated the other. And we've got the DTS on there as well to verify that. So the DTS, the distributed temperature sensing, is something we also measure, and again, all done within that same cable. So you've got accurate temperature measurements here as well. So stimulation, actually monitoring the frac operation itself is something that we've done since day one. And what this really shows is the kind of reports that are now being generated. At the bottom, you have all of the pumping data that comes from the pumping truck, shows the pressure rates, slurry rates, percentage of proppant, so on and so forth. The next stage up is the DTS, distributed temperature sensing, and you can see how if you see on the far right-hand side, where you've got each of the perf clusters within the stage, you can see how the cold water is being injected and cooling that down. So you've got flow into those perforations. But the DAS at the top really shows you very clearly which, there are 4 perforation clusters. They all start off really nicely flowing, but then after a certain amount of time, the bottom cluster actually sands out and you get no further flow. So the reason why this is important is this information is being used to optimize the treatment of subsequent wells. So you can work out exactly how far your clusters need to be apart, how far they need to be from your plugs, and so on and so forth to get accurate, optimized stimulations from there on. And these are the type of reports that we produce with stage numbers and percentages of proppant and fluid that entered each one of the stages. So one of the other kind of useful effects of this as well is if we're doing multi-well stimulations, we can actually listen to a neighboring well. So as we're stimulating one well over here, we'll listen to that neighboring well, and we get some very repeatable effects. This is what we call the cross-well communication effect. And we use this information to tell the operators how optimized their well separation actually is, if they're getting good cross communication between them. In some cases, we've seen it being the wells have been too close, and they've actually begun to push proppant almost into the adjacent well and ruin it. In other cases, we hardly see any communication at all. So we say, you know, you're leaving a space in there where you're not getting the full reservoir for oil or gas recovery. Casing leaks, we can use that fibre now in abandonment. This may be 15 years later, but that fibre's still in the well. So we can now just look and listen to it and look for things like casing leaks. Most casing leaks are continuous, but a surprising amount that we've looked at are these spontaneous leaks, which appears to be just because the ground suddenly opens, a carbonate layer or something opens, and you get this sudden injection, this is a gas producer, into the well at very high pressure, and then it closes back down again. So if you're going to run a PLT into that well, you wouldn't necessarily always catch these things because you'd have to be there at the time to spot where they were happening. So ongoing development, a very quick whistle-stop tour of the different applications, but the technology has in nowhere near kind of finished its, got to its full capability yet. Number of things we're doing. The first is data formats. James was saying earlier about getting the data into different software packages, and HTML5 was mentioned. We're working with an industry standards body, Energistics, along with a number of our competitors in this space to come up with a sensible definition of the data so that it can be transferred. But the one thing that people are always kind of concerned about is the amount of data that DAS produces. It can quite easily produce a terabyte of data a day without any problem at all. And that's only going to get orders of magnitude worse in the coming years as the technology progresses. So it's absolutely essential that you're able to process the data as you're capturing it at source. And we've spent an awful lot of time and effort doing that. So for instance, the VSP data is SegWi data in standard formats, and the other forms like flow, for instance, comes back at a fairly low data rate because you're only looking at flow at certain positions along the wellbore. As for the technology itself, as I said, we started in 2009. This was the first seismic shot we took. Of all the ones you're seeing, that's the only one that's actually doctored because it was worse than that. So we had to invert some channels to make it look that good. But what we're able to do is get an insight of how the technology could be improved. So a year later, we had a concept demonstrator. A year after that, 2011, same well, reshoot each time, and you can see the rapid improvement in 3 years. So that's kind of where we are now with the technology. Next year, early next year, we bring out version 4, which has got another 6 dBs of signal to noise, really focused on the seismic work we're doing. Better spatial resolution, so we're getting now to 4-meter spatial resolution, more channels. But interestingly, we're also working on the generation beyond that, and this is a completely clean sheet of paper, redesign the optics, everything from scratch. And the target there is to get it to the same level or better than the best conventional geophones. And touch wood, we're on course to achieving that. The current results are very, very promising. So in summary, with one fibre in one cable, you're really able now to take that and use it from everything from completions through to production and also in the evaluation of your wells using seismic types of methods. Okay, thank you.
David, thanks for that. I mean, we were having a conversation earlier about our industry being conservative when it comes to technology. Is that something you found with fibre optics? Or?
I would love everybody to adopt it faster, of course I would. But it's interestingly, when several years ago we had some consultants in and they were saying, well, we needed an insight. How long does it take for this technology to be adopted? And it was said to us, well, typically new technologies take about 30 years to get adopted in the oil and gas industry. So at that point, I thought, well, you know, I don't really want to get to my retirement and see it's going to be over. But interestingly, it was said, well, the good point is you're already halfway. In 5 years, you've got to the 15-year mark. So I think that the work we've done with Shell and the support we've done with them, and now the support of lots of other oil companies, this is a technology that's moving at an incredibly fast pace. And I think the results are what's justifying its adoption.
Okay. Please, Chris.
Yeah, very impressive progress. I saw the first slide a couple of years ago. I thought, well, it's okay. No, it really is very impressive indeed. The 4D results with the 15% NRMS, that's pretty impressive too. But I had a question about the repeatability of the coupling. You've got the fibre suspended in the borehole.
On that particular one,
but in general.
In that particular one, it was in cement behind casing, okay. So that's going to be fine. Right. What we've seen is the ones which are attached to production string, they appear to be fine. They appear to have good repeatability. Okay. Nothing seems to move in the wellbore. The ones where we do see differences is where it's temporarily deployed, so it's on coiled tubing or whatever, and that you do begin to see variations each time you do it.
Okay, thank you.
Because it's just a loose cable.
Yeah, essentially. Really impressive, and if you can get to your 2017, that'll really open the floodgates.
Touch wood.
Okay, anybody else? Yeah, so.
Hi David, thank you for the talk. As far as I know, fibre-optic cable is fairly brittle and fragile. Have there been any issues with that when deploying it in the field, and how would you address those concerns if it actually is a problem?
Yeah, I think it's a bit of a misnomer, to be honest. I mean, fibre as itself is actually stronger than steel of a wire equivalent. But the fact is the fibre is protected in very, very robust cables. I mean, this cable, I've tried for years to bend it. I can't bend it. This is stainless steel and so on and so forth. So, and these cables have been developed over about 20 years now, and the ways of handling fibre, are improving constantly. There is definitely a big push within the operators at the moment to move that on even further, because they clearly see fibre as being an enabling technology in the future, but they need the processes and the actual practical application of it to be sorted. So there are a few issues, but there are no showstoppers there, that's for sure.
Okay, yeah, please, here.
Bob Waterhouse. Suppose you had a fractured carbonate reservoir with large fractures in it, and you had the fibre optic cable running down to target depth, full depth, and you were then flowing the well. 2 questions, or maybe 3. Would you be able to identify along the length of the cable where the high flow large fractures were flowing oil into the well bore? The second point would be, would you be able to detect if there was water breaking into a well from an aquifer, say at the bottom of the well? So if you had water coming into a well, would you be able to locate that? And related to those 2 points, the third point would be, can it differentiate between somehow the kind of pressure, the density, the velocity, whatever it might be, the impact on the cable? Can it differentiate light oil, heavy oil and water according to their kind of API and viscosity and velocity type characteristics?
Sure. Okay. So first question: can we measure the difference between high flow, low flow coming through? Yes, absolutely, we can do that. So that one's a tick. In terms of can we measure multi-phase, which is essentially your next answer, at the moment, no. I don't think we've got the capability, but we are working on it. There are strong indications that it might be possible. Possibly not just with DAS, DTS and other measurands being used as well, all on the fibre. But being able to combine all of those different measurements, we think that there is potential to do multi-phase measurements within the wellbore.
Thank you.
Yeah, you would have thought the temperature one was
yeah,
pretty significant, wouldn't you?
Yeah, exactly. And the temperature and essentially acoustics pressure. So you got your P and your T. So.
Yeah, Ian. First question today, I think.
Hey, thanks, Dave. Now, of course, to make it directive, you need to have a sort of helical winding, don't you? Now, firstly, say a bit about that for future well work, and of course, in future future seismic work as well, land seismic.
Okay, so what Ian's referring to there, for those of you who don't know, is the fibre is extremely directional in its response. So it's very directional, in line, very insensitive cross-axis. That makes it ideal for VSP types of measurements where your source effort is at the top. It makes it very poor for surface seismics where you've got your source here and you're looking at reflected waves straight up perpendicular into the fibre. The way to overcome that, or the way people believed, was to helically wind the fibre, and then you get an omnidirectional response. We've been looking at that. We think we may have an alternative, which I'm not going to discuss here, but we think we have an alternative to helically winding a cable, which makes it significantly easier to do. But that's if we can do that, if we can make a perpendicularly sensitive cable, then it really does open up things like life of field seismics, PRM, and other types of applications. And it also improves it improves a lot of the downhole stuff like microseismics as well. Yeah, absolutely. Yeah.
Okay. So one final question, which is probably deeply unfair. But Quinitech obviously has a history in the defence industry, and both of the things we've heard of today come out of, remotely piloted aircraft, and fibre optics have that sort of history. And we've mentioned that they may be the two technologies of note this year. Do you see a third one somewhere that you would point to?
A third technology in the defence industry.
Yeah,
oh my goodness. For the oil and gas industry. Oh, now you put me on the spot.
Yeah, well, that's what I thought I might do. Yeah.
Dear, oh dear. There's certainly a lot of work that's being done on nanomaterials at the moment, and being able to put smart nanomaterials in wellbores, for instance, in proppant, for instance, and being able to track that proppant through the fractures. There may be a synergy between what's being done in the military sphere and what could be done in the oil and gas. But to be frank, I have to say I think that the oil and gas industry is, from my experience recently, is actually moving ahead a lot faster in those areas than the military area is. It's got more money, to be frank. It's got more money to be able to do that. Well, it did until the oil price dropped, but it.
Yeah. Okay. Good.